Hey guys, this lesson is all about chemical equations and more specifically what information you can and cannot know based on just the equation of a chemical reaction. So we're going to be looking at different ways that we identify and describe chemical equations. We're going to look at 3 limitations of reaction equations. So that's like the things that you can't know based on the equation. We're going to talk about 4 assumptions that we always make about reactions. And then some of those assumptions are things like spontaneity and rates of reaction, which we'll talk about more. You also do have to be able to predict spontaneity based on things like entropy and enthalpy. We will not be calculating spontaneity this year. That is a problem for Chem 30, but you do have to be able to predict it. So a chemical reaction, as you guys know, is anytime you have the atoms of molecules rearranging themselves through some type of chemical process. The equation of a reaction is used to indicate which molecules reacted together and what molecules were produced. And obviously we write that with the reactants on the left and the products on the right. Sometimes you might also see a catalyst included in a equation, usually above the arrow. Sometimes you'll also see energy written as either a product or a reactant, depending on whether it's an endothermic or exothermic reaction. And oftentimes you'll also see the states of matter included, like solid, liquid, or gas, or if it's an aqueous solution. So I do not require you to show states of matter or aqueous in Chem 20. See, we can get a lot of information from reaction equations, but there are limits to that. So the 3 main things that you do want to know about a reaction, but is not included in the reaction equation, is the pressure and temperature, the progress and process, and the quantities. All of those are really important. If someone is trying to replicate a chemical reaction, they will have to know that information, but it will have to be recorded separately. It's not actually in the reaction equation itself. So when we're talking about pressure and temperature, both of those can affect the rates of reaction. Certain molecules act very differently when in different pressures and temperatures, especially gas molecules. Gas molecules might be soluble at some temperatures and pressures and insoluble at other temperatures and pressures. They might start to condense. As we talked about in the second unit, gases act more and less like ideal gases based on things like pressure and temperature. Pressure and temperature also affect the speed of reactions. The higher the temperature, the faster the reaction will take place. So it is important to know that kind of stuff. The second limitation is progress and process. Progress refers to how quickly the reaction happens. And you want to know this because if the reaction happens too quickly, it can be dangerous. It can be explosive. And if the reaction is happening really slowly, you'd want to know that as well, because you want to know how long to wait until you end the experiment. And you might think that the reaction's over and end your experiment, and then your results aren't accurate because it wasn't the true end of the reaction. It was just a very, very slow reaction. And then the process refers to all the different steps that happen in a reaction. The equation only shows what you start off with and what you end with, but it doesn't show all of the things that are happening between that start and ending. So a lot of the times there might be precipitates that temporarily form and then dissolve again. There's usually a bunch of different steps that are happening between the start and end of a reaction. Think, for those of you that took biology with me, the equation for photosynthesis or cellular respiration is very basic. It starts with some glucose and some oxygen. You end up with carbon dioxide and water, or vice versa. However, if you think back to the unit that we did on cellular respiration and photosynthesis, there's a lot of other processes and reactions that are happening to get from the original reactants to the final product. So the equation doesn't always show how complex the process is. And then the third limitation is the quantities. When we write out and balance a chemical equation, we can see the ratios of the moles of the substances. So for instance, like if we have 1 mole of molecule A, we will need 2 moles of molecule B. It's like a 1 to 2 mole ratio. But you can't determine the actual quantities of products and reactants used. You can't determine mass or volume or anything like that. You can't even determine concentration based on just the equation. All you can determine is relative amounts of moles. You can't even determine actual amounts of moles. Like the equation doesn't tell you that I used 1.2 moles of molecule A. It's all just like a ratio that it's telling you. And it is really important to know the quantities of the reactants that you used if you're trying to replicate a reaction. The more of a reactant that you have, the greater the quantity of the reactant you have, the faster the reaction will occur. So it is important to know that. You also want to know the quantities of the reactants to know if it's even like feasible to do the reaction. You want to know the quantities of the products to know if it's like efficient, like if you should even bother doing the reaction. Knowing the actual quantities of the products and reactants also tells you something about its equilibrium, which we talked about in the last unit, like how strong the forward reaction is compared to the reverse reaction. All of that can be determined using quantities, but you can't determine the quantities from the chemical equation alone. You have to actually have somewhere written down, I used 44 grams of molecule A or whatever. Okay, so that's it for the limitations. And then we also make 4 assumptions about reaction equations that aren't true for all reactions. But in order for reaction equations to be useful to us, for us to be able to do things like use the mole ratio, we have to assume all of these things. So we assume that all reactions are spontaneous, fast, quantitative, and stoichiometric. So when we say that we assume a reaction is spontaneous, what we mean is that it will happen on its own. So I mix 2 chemicals together. If those 2 chemicals react, then it is spontaneous. If I have to like add heat or add pressure or add a catalyst or something like that, then it's no longer spontaneous. But as long as those chemicals, when mixed, will actually react on their own, it is spontaneous. Another way of saying this is that the reaction will proceed to completion, which means that it doesn't stop at an equilibrium. It doesn't start like moving in reverse. If we say that it's spontaneous, we mean that all of the reactant will turn into product and there will be no reactant left over. That's not always the case. Sometimes you do have that strong reverse reaction. Sometimes you do need a catalyst or an energy source or something. And we can actually calculate if a reaction is spontaneous or not by calculating its Gibbs free energy, or delta G. Gibbs free energy essentially says if something is spontaneous or not. If you have a positive delta G, that means the reaction will not be spontaneous. A negative delta G means the reaction will be spontaneous. And there are 3 things that affect Gibbs free energy: enthalpy, which is also called delta H, entropy, which is called delta S, and temperature. And they're related through this formula here. Again, we're not going to actually calculate Gibbs free energy or spontaneity this year. That is a Chem 30 issue. But we are going to learn about what these different terms mean and how to use them to predict spontaneity. So enthalpy, again, that is delta H. That refers to the energy change in a reaction. So all endothermic reactions are positive delta H. That means that they will require energy. Endothermic reactions, or any reactions with a positive enthalpy, will be non-spontaneous. They will need energy to happen. They won't happen on their own. Exothermic reactions have a negative delta H, or a negative enthalpy, and they will favor spontaneity because it is really easy to go from high to low energy, which is what exothermic reactions are doing. They have high energy reactants, low energy products. So the losing of energy is much easier to do than the gaining of energy. Again, I'm not saying though that anytime you see a negative delta H, it will definitely be spontaneous, because there are other factors to take into account. It just favors spontaneity. The second factor to take into account is entropy, also called delta S, and this refers to the amount of disorder in a reaction. So if the amount of disorder is increasing throughout the reaction, that is a positive delta S, and that would favor spontaneity. It is much more easy and more natural to become disordered. If the entropy is negative, so a negative delta S, that means that it is becoming more ordered or less disordered as the reaction goes on. It's much more difficult to organize molecules, so that would not favor spontaneity, okay? And that all comes down to the second law of thermodynamics, which essentially says that everything becomes more disordered over time unless you put energy into it. So that's true for reactions as well. They will naturally become more disordered over time. So they will naturally have a positive delta S, so that would be spontaneous. It is much more difficult and unnatural to have a negative delta S. That would require energy to have a negative delta S, which is why it favors non-spontaneity. Examples of becoming more disordered, or a positive delta S, are going from solid to liquid, or liquid to gas. Gas molecules float all over the place, quite disorganized. Solids maintain a solid shape and are very organized. Also, increasing the number of moles is more disordered. So yeah. And then the last thing to take into account is temperature. And we actually only even care about temperature when our enthalpy and entropy are not in agreement about whether or not a reaction is spontaneous. So for instance, if you have a negative delta H and a positive delta S, both of those favor spontaneity, so we don't care about the temperature. The reaction will just definitely be spontaneous. If you have a positive delta H and a negative delta S, neither one of those favors spontaneity. So once again, temperature doesn't matter. The reaction will not be spontaneous. And sorry, that is a typo there. Oops, sorry. That should say the reaction will not be spontaneous. The only time we care about temperature is when delta H and delta S are not in agreement about spontaneity. So if you have a positive delta H and a positive delta S, the positive delta H does not favor spontaneity, the positive delta S does favor spontaneity. Now we have to take temperature into account. If you have a negative delta H and a negative delta S, a negative delta H favors spontaneity, a negative delta S does not favor spontaneity. Therefore, we have to take temperature into account. So these are some spontaneity questions. Again, don't actually do any calculations. Just say for each of these whether or not they support spontaneity or not. and whether or not, for question 1, say whether or not the delta S is positive or negative. For question 2, say whether or not that would be spontaneous or not. Okay, so pause and then come back for the answer. Okay, so for number 1, we are going from having 2 molecules, the PCl2 and the chlorine, and we're ending up with just 1 molecule. So you're taking 2 things that are floating around, combining them into just 1 thing that's floating around. That is becoming less disorganized. Therefore, it would have a negative delta S, which favors non-spontaneity. 1B is the opposite. You start off with just 1 thing, end up with 2 separate molecules, so that's becoming more disorganized. So that is a positive delta S, which would favor spontaneity. Question number 2 says that energy is a reactant, which is an endothermic reaction. Endothermic reactions have a positive delta H, which favors non-spontaneity. The second reaction, 2B, says that it has a negative delta H, which favors spontaneity. That would be an exothermic reaction. And then for question 3A, as far as spontaneity goes, we start with 2 things, end up with 1. That means it would be a negative delta S. It is getting less disordered. And then the delta H that it gives you is positive. So a positive delta H with a negative delta S means that it is not spontaneous. For 3B, we have 1 molecule splitting apart into 2. That is becoming more disordered, so a positive delta S. The delta H is negative, and so a negative delta H with a positive delta S is spontaneous. This is a little chart that you might want to sketch out to help you remember. So I've got spontaneous on one side, not spontaneous on the other. Under spontaneous, I have a negative delta H or a positive delta S, and then not spontaneous is a positive delta H or a negative delta S. Okay, so that is the first assumption, that we always assume reactions are spontaneous. And then of course we can actually check that assumption based on these predictions. The second assumption is that reactions will be fast. In order to be useful, reactions need to be fast or happen at a somewhat reasonable time. We do have to be able to control the reaction rate so that it can be safe. You don't want it to be too fast, or it's unsafe. You don't want it to be too slow, or it's useless. So for example, the combustion reaction of gas in a car. If it's too fast, your car explodes. If it's too slow, your car won't run. Understanding reaction rates is important. There are a couple different things that affect the rate of reaction or the speed of a reaction: temperature, reactant concentration, surface area, catalyst, and chemical nature. We don't actually calculate reaction rates this year, but you do have to know the effects of these different things on reaction rates. So temperature, again, generally speaking, the higher the temperature, the faster the reaction will happen, because the higher the temperature, the more kinetic energy the molecules have. If their molecules are moving faster, they collide with more energy and they collide more often, which means that more of the molecules are colliding in the right orientation to actually react and with the right energy to actually react. And then reactant concentration, that just means the more concentrated the reactants are, the more quickly they will actually react. And again, that just has to do with the fact that if you have a more concentrated solution of reactants, the different reactant molecules are more likely to run into each other. If it's really dilute, the molecules are going to be really spread out and might just not run into each other. And then surface area is related to that. If you have more surface area exposed, there's more area for reactions to take place across. So yeah, usually smaller particles have higher surface area, by the way. And then a catalyst we've talked about before. So a catalyst just makes sure that the molecules that are reacting are colliding in the correct orientation for them to actually react. So yeah, it speeds up the reaction by making sure that every time the molecules run into each other, they're actually reacting. Without a catalyst, they might be like bumping into each other at angles that don't cause a reaction. A catalyst makes sure that every time they're colliding, it's a useful collision that can turn into a reaction. And then lastly, chemical nature just refers to the fact that some elements are more reactive than others. For instance, like our alkali metals or our halogens are highly reactive. Things that are in like row 13 of the periodic table would be like less reactive than 1 and 17. Yeah, so another example of that is that sodium hydroxide is more reactive than ammonia. Assumption number 3 is then quantitative. So if we say that a reaction is quantitative, it means that the reaction goes to completion. Not to be confused with spontaneous, which says that the reaction will go to completion on its own. If it's quantitative, it just means it goes to completion any which way. And by goes to completion, we mean that at least 99% of the reactants are used up. So it is a forward reaction only. You're not going to hit equilibrium. You're not going to have a strong reverse reaction. So yeah, this only works if reactions favor the forward direction. If a reaction isn't quantitative, we can't use the mole ratio. This is the reason why we can't use the mole ratio to find the concentration of hydroxide and hydronium ions when we're dealing with weak acids and bases ionizing, because they're not quantitative. They don't go to completion. They have that strong reverse reaction. But strong acids and bases are quantitative because they have that strong forward reaction, the high percent ionization, meaning that most of the acid or base will actually ionize, and you're not going to have very much of that original acid or base reactant left over. And then the last assumption is stoichiometric. Stoichiometric means that we can use the mole ratio, essentially, that you can set up the balanced chemical equation and that those coefficients actually tell you the relative amount of reactants and products that you have. And no matter how many times you do that reaction, that mole ratio should stay constant. Okay? It is important to note that the ratio can be used to compare like the moles or the molecules or the atoms of different reactants and products. It cannot be used to compare volume or mass, because just because you have like 10 grams of one substance doesn't mean you need like 20 grams of the other. If it's a 1-to-2 ratio, that means for every 1 mole of one compound, you need 2 moles of the other. Not for every 1 gram, you need 2 grams of the other. Okay, and that's it. Those are your assumptions. So make sure that you're reviewing the 4 different assumptions as well as the factors that affect reaction rate and the different things that affect spontaneity, and also your 3 different limitations of reaction. reaction equations.